In this problem, we are looking at a student whose performance from day to day sort of oscillates according to a Markov chain. In particular, the student can either be in state 1, which is a state of being up to date, or in state 2, which is a state of being kind of fallen behind. Now, the transition probabilities between these two states are given by the numbers here, which is 0.2 from state 1 to 2, 0.6 from 2 to 1, 0.4 from 2 back to 2, and 0.8 from 1 back to state 1. The quantity we're interested in calculating is this notion of first passage time. Let me define what that means. Suppose we are looking at a time horizon of time 0, 1, 2, 3, and let's call the state of the Markov chain x of t. Suppose we start from the chain being in state 2 here. Now, if we look at a particular sample path, let's say 2 and 2 again on day 1, and 2 again on day 2, and on day 3, the student enters state 1. So in this sample path, we start from time 0, and time 3 is the first time we enter state 1. And we'll say that the first passage time, namely the first time we enter state 1, in this case, is equal to 3. More formally, we'll define Tj as the first passage time to state 1, conditional on that we start from state j at time 0. Now, this quantity, of course, is random. Depending on realization, we have different numbers. And we are interested in calculating the expected value of T2. That is, on average, if we start from state 2 here, how long would it take for us to enter state 1? Now, to calculate this quantity, the following recursion will be very important. The idea is we don't know exactly what T2 is, but T2 has to satisfy certain recurrent equation, namely T2 must be equal to 1 plus summation j equal to 1 to 2 p2j tj. Now, let me explain what this equation means. Let's say we are at state 2. Well, we don't actually know how long it's going to take for us to enter state 1. But we do know after one step, I will be going to some other state. Let's call it state j. And from state j, it's going to take some time to enter state 1 finally. So this equation essentially says the time for us to first enter state 1 from 2 is 1, which is the next step, plus the expected time from that point on to enter 1. So that constitutes our recurrence relationship. Now, by this definition, we can see that this is simply 1 plus P21 times T1 plus P22 times T2. Now, the definition of Tj says T1 must be 0 because by definition, if we start from state 1, we are already in state 1. So the time to reach state 1 is simply 0. So this term disappears, and we end up with 1 plus P22 T2. If we plug in a number of P22, which is 0.4 right here, we get 1 plus 0.4 T2. Now, we started from T2, and we ended up with another expression involving numbers and only one unknown, which is T2. Combining this together and solving for T2, we get T2 equals 1 divided by 1 minus 0.4, which is 5/3. And that is the answer for the first part of the problem. In the second part of the problem, we're asked to do something similar as before, but with a slight twist. Here I copied over the definition for tj, which is the first time to visit state 1 starting from state j at time z, and time t equals 0. And the little tj is its expectation. And here we're going to define a similar quantity, which is t1, let's say star, defined as the first time to visit state 1 again. So that's the recurrence part starting from state 1. 1 at t equals 0. So this is the recurrence time from state 1 back to state 1 again. As example, again, we look at t equals 0, 1, 2, 3, 4. And here, if we start from state 1 on time 0, went to state 2, 2, 1, 1 again. Now here, again, time 3 will be the first time to visit state 1 after time 0. And we don't count the very first 0, and that will be our t1 star. So t1 star in this particular case is equal to 3. Okay, same as before, we'd like to calculate the expected time to revisit state 1. Define little t1 star, expected value of big T1 star, and we'll be using the same recurrence trick through the following equation. We say that T1 star is equal to 1 plus j from 1 to 2. Now, since we started from state 1, this goes from 1 to state j, P1j, and tj. Again, the interpretation is we started at state 1 at time t equals 0. We went to some other state, call it j, and from state j goes around, and after time expected value tj, we came back to state 1. Here, and as before, this equation works because we are working with a Markov chain whereby the time to reach some other state only depends on the current state, and that's why we're able to break down the recursion as follows. We write out the recursion, we get 1 plus P11 T1 plus P12 T2. As before, T1 now is just the expected first passage time from state 1, and by definition it is 0 because if we start from state 1, it's already in state 1 and takes 0 time to get there. So again, like before, this term goes out, and we have 1 plus 0.2 times 5 over 3. And this number came from the previous calculation of T2, and this gives us 4 over 3. So this completes the problem, and just to remind ourselves, the problem, kind of the crux of the problem is this type of recursion, which expresses certain quantity in one incremental step and followed by the expected time to reach certain destination after that one step. And we can do so because the dynamics is modeled by a Markov chain, and hence the time to reach a certain destination after this first step only depends on where you start again, in this case, state J.